हेलो स्टूडेंट्स, कैसी तैयारी चल रही है? वेलकम टू माय चैनल. If you have not subscribed my channel yet, please subscribe by pressing the subscribe button. You can also ask your friends to subscribe my channel. Today I shall discuss one important property of solids, that is electrical properties. Electrical properties are one of the important properties shown by solids. The electrical properties of solids are due to the presence of free electrons. On the basis of electrical conductivity, solids can be classified into three types. First is conductors. First one is conductors. Second is insulators, and third is semiconductors. In case of conductors, the conductivity is very high. It is of the order 10 to the power 7 ohm inverse meter inverse. Conductors have conductivity of the order 10 to the power 7 ohm inverse meter inverse. All the metals have very good conductivity, and their conductivity generally ranges from 10 to the power 4 to 10 to the power 7 ohm inverse meter inverse. Insulators are the substances which have very low conductivity. Their conductivity can be as low as 10 to the power minus 10 to 10 to the power minus 20 ohm inverse meter inverse. For example, wood is an example of insulator. In case of conductors, for example, silver, copper, aluminium are good examples of conductors. Semiconductors are the substances which have conductivity intermediate between conductors and insulators. They have conductivities of the order 10 to the power minus 6 to 10 to the power 4 ohm inverse meter inverse. They have conductivities intermediate between conductors and insulators. Some examples are silicon and germanium, which are known as semiconductors. Now, the conductivity in case of conductors, we can explain the conductivity in case of conductors and semiconductors and insulators. Electrical conductivity in case of conductors. The electrical conductivity in case of conductors or metals is due to the presence of valency electrons. The atomic orbitals present in metals combine to form molecular orbitals. The atomic orbitals combine to form molecular orbital. For example, in case of lithium, we have 1s2, 2s1. Electronic configuration of lithium is 1s2, 2s1. Now, in case of lithium metal, there are 10 to the power 23 lithium metals. These lithium metals are of the order 10 to the power 23. These lithium metals, these lithium atoms have atomic orbitals. The atomic orbitals combine to form molecular orbital. And these molecular orbitals are so closely spaced that they form a band. For example, here another lithium metal which have 1s2, 2s1, 1s2, 1s2 combines atomic orbitals having identical shape and nearly equal energy combine to form molecular orbital. 1s and 1s combines to form molecular orbitals. Similarly, 2s and 2s combine to form molecular orbitals. And there are many atomic orbitals available, so the molecular orbitals are so closely spaced that they form bands. They form bands like this. 1s band, first is 1s band, and here is 2s band. 1s band is completely filled, but 2s band is half filled. Now the energy gap between valency band and conduction band or empty band is small. So the electrons can easily flow from valence band to conduction band. This is valency band and this is conduction band. The electron can easily go from valence band to conduction band on application of electrical potential. So they are good conductors of electricity in solid state as well as in molten state. But in case of insulator, if we take insulator, the energy gap between valency band and conduction band is very high. The energy gap is very high. So electrons can not move from valency band to conduction band even at very high temperature. So they do not show electrical conductivity or very poor electrical conductivity. Now we can also explain the electrical conductivity in case of semiconductors. In case of semiconductors, electrical conductivity in case of semiconductors. Semiconductors are substances which have electrical conductivity intermediate between conductors and insulator. Here the energy gap between the filled conduction band and empty valence band. This is the valence band, this is the conduction band. Eg, this is known as energy gap. The energy gap is low. There is a low energy gap between the conduction band and valency band in case of semiconductors. So by heating, if we supply heat energy to semiconductors, then the electrons present in conduction band can easily go to the valency band. So they show electrical conductivity upon heating. Alternatively, if we dope these semiconductors, for example, silicon, germanium, with group 13 or 15 elements, group 13 or 15 elements, then their conductivity also increases due to the presence of impurity band. In this position comes the impurity band, due to the presence of impurity band between the energy gap of conduction band and valency band. This silicon and germanium can be doped with group 13 element, for example with aluminum, boron or aluminum, or group 15 elements, for example with nitrogen or phosphorus. If silicon is doped with group 13 element, then one vacancy is generated, since silicon has 4 valency electrons, and if we replace one silicon by boron, if we replace one silicon atom by boron atom, here are present silicon, these are the silicon atoms. In case of boron, it has 2, 3 electronic configuration is 2, 3. Now in case of boron, since there are only 3 valency electrons, in case of boron only 3 valency electrons are present, so 3 valency electrons forms covalent bond with 3 silicon neighboring silicon atoms, but the fourth position remains vacant and it generates a hole. It generates a hole or vacancy. Now, one electron present inside the crystal lattice may come here to fill up this vacancy, and we can see that there is conduction due to the movement of holes, or in opposite direction the movement of electrons. Similarly, we can dope these pure semiconductors are known as intrinsic semiconductors. They are known as intrinsic semiconductors. When they are doped with boron or aluminum, nitrogen or phosphorus, they are known as extrinsic semiconductors. Similarly, we can dope silicon with group 15 elements. For example, if here is a silicon atom, silicon has valency 4, it is bonded with 4 silicon atoms like this. Now if we replace one silicon atom by phosphorus group 15 element, then the electronic configuration of phosphorus is 2, 8, 5. There are 5 valency electrons in phosphorus. Now the 4 valency electrons of phosphorus combines with 4 silicon atoms to form single covalent bond, but fifth valency electron of phosphorus remains unbonded. Now there are many phosphorus atoms inside the silicon crystal, therefore there are many electrons present inside the crystal lattice, and upon application of electrical field, these electrons move to the opposite electrodes, so there is electrical conduction. These type of extrinsic semiconductors are known as P-type semiconductors, since here the conductivity is due to the flow of holes or vacancies, so it is known as P or positive type extrinsic semiconductor. Similarly, here the conduction is due to the flow of electrons which have negative charge, therefore this is known as N-type semiconductors. It is known as N-type semiconductors. So we have discussed about electrical conductivity in semiconductors. In case of semiconductors, the energy gap between valency band and conduction band is very low, and upon heating, the electrons can easily transfer from valency band to conduction band, and therefore semiconductors show electrical conductivity upon heating. Conductivity increases upon heating. Similarly, if we dope semiconductors such as silicon or germanium with group 13 or group 15 elements, they are known as extrinsic semiconductors. The conductivity of these semiconductors such as silicon or germanium increases by doping. If we dope with group 13 element here, for example, if we take boron, then in case of boron, there are 3 valency electrons. Therefore, 3 electrons forms covalent bond, single covalent bond with 3 neighboring silicon atom, but fourth position remains vacant. So a hole or vacancy is generated, which moves inside the crystal lattice upon application of electrical field. This is known as P-type semiconductor. Similarly, if we dope silicon with group 15 elements, for example phosphorus, then 4 electrons of phosphorus atoms combines with neighboring silicon atoms, but fifth valency electron remains unbonded, and upon application of electrical field it moves towards the anode. So here the electrical conductivity is due to the flow of electrons which are negatively charged, therefore it is known as N-type semiconductors. So today we have discussed about electrical conductivity, classification of solids on the basis of electrical conductance. There are of three types: conductors, insulators, and semiconductors. Conductors have very high electrical conductivity. In case of insulators, conductivity is very low. In case of semiconductors, the conductivity is intermediate between conductors and insulators. Again, we have discussed about semiconductors. There are of two types: intrinsic semiconductors. For example, pure silicon and germanium are known as intrinsic semiconductors. They have very low conductivity. When they are doped with group 13 or 15 elements, they are known as extrinsic semiconductors. Extrinsic semiconductors can be of two types: p-type semiconductor or N-type semiconductor. In case of p-type semiconductor, conduction is due to the flow of holes or vacancies. In case of N-type semiconductors, conductivity is due to the flow of electrons. Thank you for watching my channel. Your comments are welcome. You can suggest any other topic you want to discuss later. Please subscribe my channel and also ask your friends to subscribe my channel. Thank you once again.